the first workshop session of Protocol Berg. Thanks a lot for signing up to being here for 40 minutes. Though of course there's no guard dogs at the exit that will actually prevent you from leaving. But this is a workshop. As you probably guess, multi-purpose consensus implementations are a thing that is a little bit difficult to demo on a stage. So one of the things I'd like to do here for the 30 minutes is to make this as interactive as possible. If you have any questions, remarks, spicy comments to make, feel free to shoot a hand, or if you don't like to be picked on, put something on the QR code is not here anymore. There was a QR code that allowed you on Meerkat to push questions to me, and that's something I can monitor as well. Okay, so let's see if we can have slides. Yay! All righty. So why on earth am I talking about those things? And the answer is I'm an engineer. I have through various projects been doing that, doing consensus implementations for a little while. I was part of the Libra project in 2018. I started working on an implementation of Blockmania. That was my first DAG-based protocol back then. I've contributed to a few consensus protocol implementations, and I was the lead of Narwhal into the first year of Mysticeti Labs Sui blockchain. Then I took a couple of years of break to work on ZK, nothing related to consensus, and then in the last 6 months or so, I've been consulting with a number of teams that are interested in that kind of protocol again. And what I'd like to share here is my experience in finding what's available in open source repositories to make that stuff go really, really fast and really efficiently for all the blockchains that we know and love. But from the point of view of an engineer, what has become a commodity is research talks on consensus protocols that are relatively fancy and advanced and optimize on latency and throughput metrics. This is not this talk. If you want that kind of talk, there are several. Nikita is giving one at this very conference. There are many at many other conferences, and you will find all the content you want. Here, this is really an engineer's perspective on how maintainable is the code, are the code bases, how implementable are those algorithms. It's going to be vastly colored by my experience, but by also scouring the GitHubs for finding what's interesting these days. Okay. But first, why would you even care about multi-proposal consensus? And there's the modern answer and the less, the original answer for why those things were developed. The usual challenge that we have now is noticing that in decentralization now we have blockchains. Those blockchains are popular because they are popular. People start looking at order flow on those blockchains and try to see if they can exploit that knowledge for financial profit. That leads to MEV, which and potential censorship. And we want to incentivize and incentive align all of the participants of our blockchains. Okay. Now, if you have multiple proposers that are all able at the same time to propose the content of a block, a lot of those issues become easier to deal with. They are not solved magically by the presence of multi-proposers, sadly, I only wish. But they become easier in ways that we're going to detail a little bit more. Roughly because if you want a transaction to not be included, you now have to bribe multiple proposers that are susceptible to include this. This is absolutely not why any of this was developed. Any DAG protocol you've been interested in, any multi-proposer consensus protocol you've ever seen was developed for one reason that is in the next 4 slides. So here's what happens when you have a single proposer. You have a block. You need to disseminate that block through, let's say we have 4 authorities, so 4 validators. Okay, this is the classical broadcast dissemination, and this is the nitty-gritty accountant's view of what you're going to need to do with your network. Your emitter, your block proposer, is going to need to, assuming that you're doing synchronous messaging on the network, we're taking all the simplifying assumptions here. If you can think of a simplifying assumption regarding the network, it's being used here. So your proposer needs to have a bandwidth of 3, assuming your block is of size 1, to be able to send the block to everyone, all 3 others, in a delay of 1. Okay. Every receiver needs to have an incoming bandwidth of 1 to be able to receive the block. And your throughput, once you've done that, is 1. Great. Now, here's what it looks like when you have multiple proposers. You run the same thing, but everybody is simultaneously an emitter and a receiver at the same time. Now, you have 4 validators. They're each sending 1 block to all the other 3, and each of the other 3 is receiving 3 blocks from all the other authorities. Okay? And this graph is the reason that all of this work was made. It's basically because on the emission side, and in fact, everybody being an emitter and a receiver, everybody is looking at the same graph. You need, in order to send this in 1 delay, you need to have a bandwidth of 3. You need an outgoing bandwidth, an incoming bandwidth of 3 to receive all the blocks, and the global throughput of your system is 4, not 1. You have now 4 blocks that have changed hands. So your dissemination goes a lot faster. A lot of the thinking around DAG-based multi-proposer consensus algorithms is often modeled through communication complexities. The communication complexities are the same as any other consensus algorithm. They do not improve, but you are running that over a vaster amount of data so that you amortize and pipeline a lot of the messages more efficiently by making everybody have the role of an emitter concurrently. Yeah. Oh, the graph is absolutely not supposed to be empty. This seems to be a contrast issue. Okay, so then we're going to imagine that we have a bar graph where the output is the output is 3, the input is 3, and the global throughput is 4, right? Because this is the relevant aspect of things. You need a bandwidth of 3 to be able to send 1 block to 3 people at the same time, and you need an incoming bandwidth of 3 to be able to receive 3 blocks from 3 people at the same time. Right? Because you globally have now 4 blocks that have changed hands, that are disseminated, and that are ready to go for everybody involved, right? So each validator has received 3 blocks from the others and has shared their 1 block. So the whole idea of those algorithms is to amortize the cost of running your consensus by running it simultaneously in many places. Now, if you are as, yeah. Yes, you're completely assuming to say, hey, this graph has a throughput of 4, that the blocks are not overlapping, there's no duplication in the blocks. Now, if you're feeding your validators based on the same mempool, and if they're looking at the same mempool, they can pick the same transactions to include in the block. And in that case, you have a deduplication problem. You're completely correct. Now, there are mitigations for that, right? Mitigations such as, let's not have a mempool. Let's direct users to validators at random. They give their transaction to the validator, and you assume that the users are only connected with 1 single validator. We'll talk about other ways of dealing with that problem. Okay, Now, if you are a library rat, you can go into the old stories of what has happened in that line of research. You'll learn about MIR-BFT, the origins of multi-consensus, and here you'll see that the philosophy is really, let's run multiple consensus algorithms in parallel. We have a horrible, horrible communication complexity. We have a very good theorem telling us that we will have, whatever we do, a horrible communication complexity. Let's amortize the bandwidth by running it in the emitter and the receiver side of things simultaneously at all places. Hashgraph is probably, in 2016, was probably the paper that in the implementation, the concrete implementation that popularized a lot of this. But the insights are a lot older than this. In fact, we'll see references going all the way back to the 90s. But this is about modern multipurpose consensus. And so basically, in this entire talk, if there's only one thing to retain, it's probably why is it that we don't see multipurpose consensus everywhere, considering that it has become, over years, a lot faster and a lot easier to integrate those implementations. And the reasons that I could fathom are pretty much on this slide. First, if you have several multiple concurrent proposers, you can't pre-execute the result of your block. You don't know in advance what the entirety of your global addition of transactions to your blockchains is going to look like. So if you are dealing with a blockchain that strongly assumes that you must make a claim to the result of execution before you propose anything, then you're in trouble. That's not how this works. Why? The proposers are concurrent. You don't know what the others are going to propose, therefore you have no idea, no ability to simulate what that's going to be. I would argue that's a feature, right? So it's a feature that prevents MEV, that gives you a lot of throughput, but yeah, no, I mean, sorry, we're not going to be able to pre-execute things for you. The other thing is the existing implementations, notably the one of SWI, which in terms of implementation is the dominant one. There's research up the wazoo, but the people who are implementing this in production are mostly SWI, have no mempool. It's really the paradigm of you get connected to one validator and you submit your stuff to one validator. The validators don't feed themselves on the basis of a single mempool. Now, the mempool is used for decentralization in and of itself. There's many ways to organize and design things, but if you really need a strong assumption of a mempool, you need to be a little bit more clever when doing a multiproposer implementation. That's where the next barrier looks like. And then, yeah. No, that's not a thing I said. I just said that I can't give you a claim to the results of execution before in my proposal. So when I'm making a block proposal, I can't tell you what will be the state of the blockchain after having integrated those transactions because I don't know in advance. There's multiple concurrent proposers. If I'm going to be ordered first, and even if I'm going to be ordered first, what the others are going to be proposing. So at end of block, I can't tell you what this is. I do not claim that the fact, which is something you will find very often, that because you have no mempool, you have no MEV. That's not a thing. And like everybody that has open crypto Twitter and searched the word Solana is well aware of this. Solana has no mempool. You might have heard of Jito. You can reintroduce MEV with a multiproposer consensus algorithm. That's not a problem at all. Okay, so if you are going to go for a mempool, if you really do care about mempool, you're going to need to figure out how to get through the problem that our friend highlighted at the beginning of this talk, which is, okay, you're going to need an assignment of transactions to validators. Who's going to be the proposer of that transaction? And ideally, can we have not everybody, not 130 validators propose that same transaction? Because otherwise all the throughput and the bandwidth gains that we've made are immediately lost, right? Those are really the modern problems. But the good news is once you solve those, you're done. Why? Because these days we have everything, and I do mean everything, on this line of research. Like, we have, we're not going to go through this, but like, if you want formal proof of safety of those algorithms, they exist. If you want people that have looked at liveness bugs, if you want competition between several lines of research, I'm going to be very SWE influenced here, but Aptos has Shoal and Cordial miners that are also fantastic multi-purpose consensus research papers. You have criticisms of subtle details on data availability. And you even have some keynotes from the SWE team explaining some of their line of research and engineering challenges. So a lot of this exists, and you have as much background, I would say, on multi-purpose consensus implementations as you have in single-purpose consensus and implementations. So really, figuring out the mempool is the only thing that's left. I'm even not mentioning a crap ton of research that still exists in that line. There's an entire line of research on motorway, autobahn, sailfish, starfish. They're in the same conference. Nicola Polianski will talk about this. Okay, I said, so if you are looking for research papers, you can kill a printer with what exists right now. It used to not be the case as early as 3 or 4 years ago. But now we have a very nice thing called Mysticeti. That's a development of the last 2 years, and it's basically a Narwhal consensus algorithm with virtual voting. So Narwhal was multi-purpose consensus algorithm initially developed at Libra. This is the thing that has happened in the last couple of years. Initially in the Libra project, Narwhal was the result of the research team at Libra. The engineering team had already decided that they were going to run a single purpose consensus algorithm called HotStuff. So as a research team, what do you do to be relevant? You're not going to propose another consensus algorithm. They've already made their choice. You basically propose a very fast mempool, so that this fancy single purpose consensus algorithm now just deals with small, teensy tiny hashes that refer to stuff that is already in your mempool. So Narwhal was developed with a primitive of reliable broadcast. And if you implement reliable broadcast as a consensus engineer, you're in for a relatively subtle implementation. Mysticeti went and said, hey, let's do exactly none of that. By noticing that the pattern of communication can actually be different. And this is what your reliable broadcasts look like. To do one round of block proposing in Narwhal, you had to be a proposer that submits, broadcast a block or block header, depending on how you do your data dissemination, to everyone. Everyone sends you back a vote. You're collecting those votes, collecting at least 2f+1 votes by stake, and creating an object called a certificate, which is the sum of all those signatures. And then you send back that certificate to everybody involved to say, hey, see, everybody has seen my block. It is now completely enshrined within the common knowledge of the validators of this blockchain. It makes a ton of sense if your goal is to devise a mempool that contains a bunch of blocks so that you can have another consensus algorithm that afterwards feeds itself on the basis of that mempool. Because now you're extra super duper sure that your block is data available throughout the validators that are involved in this. But in 1990, network engineers, not in the consensus community and having, of course, no idea what a blockchain would even look like, were already researching consensus. And they had an idea saying, hey, we can do a thing called virtual voting. Meaning if sequentially, if I do another proposal that comes after the block that I'm interested in, I can basically refer to the hash of that block header and add it to my own proposal. And then my own proposal will implicitly contain a block for that a vote for that antecedent block header. That's the idea of virtual voting. The idea is we're going to pipeline messages. By the way, pipelining is a big hammer, and everybody that does consensus these days uses pipelining as if everything was an AL. So the idea of pipelining is really fundamentally, you don't need to send back signatures, you don't need to aggregate them like this, you just need to notice what everybody is saying, and in what everybody is saying, you need to notice the small hashes that contain votes for things that have occurred before in the conversation. This is the strong basis for the hash graph consensus algorithm, if you're familiar with the literature. And this is the main ID that was reused by Mysticeti, which means that the messaging looks like this right now. So just to put that back on, you send a block header, send back vote, send certificate. Ouch. Now it looks like this. Send blocks. And then send blocks. And then send more blocks. Ad infinitum. This is really nice. Because it meant that in the concrete implementation of a Narwhal consensus algorithm, you had to take care of data dissemination. Now that's already 80% of your code. Once you had done that data dissemination, you did very fancy block headers. Those block headers also had messages that were received in response, that were votes. You assembled certificates using signature aggregation and send back those certificates. Now, all of those messages have different sizes. They also have slightly different reliability guarantees. If your block header is not working, because in Narwhal we're working with something called threshold logical clocks that I'm not going to bore you with, you really need to retry sending that block header as long as possible. If a vote doesn't make it to the proposer, you can assume that up to 1/3 of your validators are Byzantine. It's just a faulty case. It's not the end of the world. So reliability guarantees are different, which means you have different code paths for those different messages. Network prioritization becomes a mess. We're going to go back to how you need to support streaming at a low level if you want to implement this efficiently. And so that added significant implementation complexity. Now, well, with Mysticeti, we have one type of sign block for all operations. The consensus is essentially one fanciful function on one data structure that manages the DAG that we're going to go into relatively quickly. And every validator deals with the same kind of message all of the time. So concretely speaking, this is a heck of a lot easier to maintain, test, optimize, implement, audit. Why is this interesting? So first, I wanted to credit the engineer. Now don't get me wrong, the researchers that have worked on all of those papers, fantastic. But the engineers don't get enough credit for this. You get implementations that are tremendously simple. You will get a talk tomorrow by Lefteris on something called Walrus. I don't really know what Walrus is, but he's also he's also worked on some of that the research line of things. But the engineers that have worked on this have left a lot of very nice little pearls in a code base that is open source and that you can source and use in modular ways. We're going to get into specifically how you can use it in modular ways. So concretely, we now have graph representation. My slides actually managed to come out not too bad. How does that work? Okay, so the implementation, I have 6 slides and I promise there's no 7th on how the inner workings of a DAG allow you to think about certification and consensus in a relatively simple way. This is fundamentally about dealing about one in-memory data structure that is dealing with a virtual graph representation in an adjacency list way. So the idea is everybody works in rounds. I'm not going to talk about round synchronization. This is a thing called threshold logical clocks. This is relatively easy to figure out. But basically, you're going to assume with me that the nodes have a way to understand. Here we have 4 nodes represented as lines with their proposals. And we have 5 rounds represented in columns. The rounds go from left to right. And each node is a proposer at every single round. When somebody decides to not acknowledge, through including a hash of a prior proposal, a prior participant in their block, we're going to call this a blame. And this is just vocabulary. So in your proposal, you are supposed to acknowledge prior proposals from other validators, and you're supposed to acknowledge 2f plus 1 of them by stake. So you have to have 2f plus 1 worth of hashes. So in our case, assuming everybody has the same stake, 3 hashes in your block proposal. Every time you have a hash in your block proposal, I can draw a very nice green arrow. And that green arrow says, yeah, I've seen the thing that came before me, and the thing that came before me was something that was kind of sort of, if you squint, valid. I kind of like it. That's an acknowledgement. Now, if you get 2f plus 1 acknowledgements, you get a certificate. Mysticeti works by saying, hey, if I have 2f plus 1 worth of the network that considers that your block is bad, we can skip it. There's no way that we're going to commit this. The majority of the network that makes sense, the majority of the network considers you should be excluded. If, on the other hand, I get 2f plus 1 of the network that certifies your block, we're going to commit that thing. The L3A block here needs to be committed. And in some cases, we're not going to be able to make a decision. Here, the L3A block doesn't really have the pattern that we want in the next few rounds. And we're going to leave that decision to the following block. I'm grossly oversimplifying here, mostly because there's research papers explaining this in detail, and this is not really the talk to explain this. But by leaving this decision to future rounds in the construction of the DAG, we're basically be able to mitigate the lack of acknowledgements that can have been created by Byzantine leaders, by networking defects, while at the same time not stopping the construction of our DAG. Okay, so obviously this is not loading. This is the picture that is usually not shared in any research paper on Mysticeti. Any research paper on Mysticeti is telling you we have a much better latency because we're not using this reliable broadcast. Remember, a reliable broadcast said, hey guys, I have a block. Everybody votes for the block. I assemble a certificate. Hey guys, I have a certificate for my block. That takes a while. If you're simply sending blocks and assuming that acknowledgements for that block will come afterwards in other block proposals, you're dividing your latency by 2. What that concretely means is the latency to actually commit, the latency to finality, crashed with Mysticeti. Now, that's great and everything. This is not the benchmark you have on the slide. And this is not the benchmark you should be interested in. This is not a research benchmark, guys. There is no reason whatsoever that a Narwhal implementation should be, and this is the one in orange and blue, Narwhal, bull shark, small details on what the difference between the two is. There's no reason whatsoever for why Mysticeti should have better throughput. Except it does, by a factor of 3. That is engineering. The video that I did not load and that I had before is a video by the researchers acknowledging there is no reason for this whatsoever other than implementation. And the result of this is network has become simpler. there's now a single message form, and the only thing you have to optimize is dissemination. That is tremendously important, and this is something we can have for free in an open source code base near you today. All right, so which open source code base? There's two implementations of Mysticeti today. There's a Mysticeti research repo that I will actually advise that you do not look at. Mostly because this is the engineers using it as a playground to learn how to implement Mysticeti. And you have a three implementations that is really interesting for you and was interesting for me at the beginning of this year. The consensus is completely modularized away from the chain. It's its own little directory where everything is different. The network and storage are also modularized away, which means if you want to use that on a different networking stack, it takes you 10 minutes. If you want to do that on a completely different storage stack, it takes you 10 minutes as well. There's very nice trays that are completely aware of that. Now, there's one extra thing that is in there, which is you might have heard that some people do Byzantine consistent broadcast. Oh, sorry, you are not living in a library? Some people are doing things that look like fastpath or linear or pod or delta. Okay, nobody has heard of any of those things. Work with me, people. The point is, there's an extra protocol, fastpath, that exists on top of all of this classical consensus stuff that I'm going to talk about at the end if I have a little bit of time. That part isn't modularized, but on the other hand, it wasn't implemented in this code base before January. So if you fork something that was in January, you don't even have to look at it. The only thing that needs to be re-implemented if you want to use a consensus module from SWI is really the epoch change. And that kind of sort of makes sense, right? Does anybody have an idea of why it's very, very difficult to modularize an epoch change out of a consensus implementation in a modern blockchain? Not really finality, because finality in all of those proof of stake algorithms. Now, of course, if you're thinking Bitcoin, Ethereum, there's a long history and legacy of finality in the code bases, because they've had colored histories with respect to finality. But here we're talking modern proof of stake algorithms. So things that are using Cosmos SDK era forward kind of have the same assumptions around Cosmos, around finality. Oh, the epoch change is when you change your quorum of validators, right? So you have, let's say, 120 validators, and then you have some guys that want to retire, some guys that want to participate. You need to change the number of participants in your consensus algorithm. Yeah, so we're getting into that general area, which is first your protocol incentives look completely different, but mostly they are mostly managed by your chain itself. That is, you're using smart contract to figure out how much everybody should be paid in order to get stake rewards, for example, right? Which means that your implementation of epoch change is actually dominated by your sourced from your execution. You decide in smart contracts who gets to join in, who is in, who is out, and that's the source of your information. You kind of need to pass that information, which is, and your execution here is the source of truth, meaning your blockchain is the source of truth, all the way back into your consensus, and then operate an epoch change. But so that part isn't really modularized yet. It needs a little bit more custom work, but mostly if you're writing a completely independent consensus algorithm, the way you implement it is by saying, hey, that stuff can be restarted with a completely new stake table. The stake table is canonically the list of validators that are involved in your consensus and how much stake they have. It's basically the name of the game for who the participants of the game are. Okay, now, in there's a couple of tricks of the tricks. I have just 2 slides on this that I want to go over very, very quickly, but we really have good data on how that actually makes a difference on performance. Number one, support some sort of streaming to avoid head-of-line blocking. There's a bunch of code bases that I've looked at that have gone through the same story of having yet another networking implementation that didn't work out, and that they replaced with something that supported some avoidance of head-of-line blocking. The rough idea being, especially if you have, as I strongly advise you do, direct connections between validators, you're going to request stuff out of those validators that will have different priorities, and you're going to want to manage those priorities in parallel from a networking standpoint. If you have an implementation that doesn't support streaming, your low priority request that got into the pipe ahead of time is blocking your high priority request, and it gets a little bit problematic. Second thing, signing costs when you're looking at choosing a cryptographic signature algorithm. Fun stuff. Verifying a BLS signature still takes at least 20 times the time it takes to verify an ED 25519 signature. And that's even without looking at the batching algorithm, the batch verification algorithm that exists on ED 25519. Which means if you're not verifying 20 ED 25519 signatures at least, BLS, bad idea. The main difficulty in your implementation of consensus is now a thing that exists in every single consensus code base, which is a causal completion engine. You're doing synchronization, and you are basically looking at a block header, a vote, a certificate, whatever you have in your consensus algorithm, and it refers by hash to something prior, right? Hash pointer to a prior block. And you have no idea what that is. For two reasons. One, you got messages out of order. Yeah, networks work like that. It happens. That's what I would call short range synchronization. You're just missing a few antecedents to be able to interpret the current message. You park the current message, request the antecedents. Once you have them, you interpret that message in question. Second thing, somebody woke on your power plug, you just restarted after 3 hours of downtime. You have no idea how to interpret the current message. And then when you ask for the prior message, you have no idea how to interpret that. And then when you ask for the prior message before that, you have no idea how to interpret that, all the way 3 hours into the past. Do not use the same protocol for this. Sui, fun story, Sui actually used the same protocol for this initially. Immediately, Aptos came up with benchmarks showing that when you you drop X% of messages, the Narwhal latency crashed immediately, mostly because of that problem. Synchronization causal completion engines are absolute drivers of your consensus performance. You want to split two engines, one for short range, one for long range synchronization. When you restart your node, do not start doing causal completion, especially in the DAG where you have five different prior block pointers on a regular basis. Fun stuff. IRO has done a very funny DAG thing that minimizes what is the main driver of complexity here in short-range synchronization, which is the number of messages that you exchange with others in order to be efficient. Okay, Byzantine consistent broadcast. Well, since nobody has actually asked me about mention this, we're going to skip eagerly over this entire section. But ask me about it after that. The rough idea is consensus. There's very strong theorem saying that whatever your consensus algorithm looks like, you're going to have a worst case complexity that is at least quadratic. And do we absolutely need to do this to run a blockchain? And the answer is, if you are willing to restrict severely what running a blockchain looks like, you can actually do better. There's a bunch of projects that work on this. The Sui fastpath is exactly an implementation of that. There's Linear, Pod, Delta, that have gone a new a new popularity in the last few years. And I have, I'll share my slides. I have an entire blog post around this. Read the blog post. We're going to skip and go back to consensus. Cool. So we now have, and this is the takeaway that I want to leave you with on what does the future research, the future engineering research or applied research opportunities look like in this space. The thing is, now everything is a broadcast. We really don't need to have very complex code bases that clearly separate data dissemination of a particular block from block headers anymore. We can just optimize for, hey, I have this new block that I want to add to a common DAG that we are going to reason over. And I would like to disseminate it among the participants. Now, the Narwhal implementation, the Mysticeti implementation is broadcasted as I believe, 279,000 transactions per second in production, not a research benchmark. Now, that's currently implemented as a very basic point-to-point broadcast, open one connection per participant, and that runs over HTTP2 streams on Tonic. This is not the most clever implementation in the world. Not the most optimized in the world. So this is accessible to everyone. Now, the problem is, can we go faster? Now, there's a very strong answer from the Solana community that says, okay, Turbine, we're going to read Solomon. The problem with that kind of peer-to-peer implementation is it depends on stragglers, and depending on your network topology, you're going to have one validator that will be on the other side of the world, not gonna have enough direct bandwidth between your emitter and the receiver to actually go really well. It would go a heck of a lot faster if you passed on your block to somebody else, and if that somebody else was to relay it to your destination. Cool. Solana has worked on Turbine, which basically works over re-Solomon encoded shards. So you erasure code your block, and then you transmit that over a relatively fancy gossip network that allows you to do this. This is somewhat straggler sensitive because it depends on the little min cut and has some topology problems. Turns out that those implementations can get fiendishly complicated. I'll leave you to another tool to figure out what that looks like. But we have there's new directions into optimizing this, and some of which are brought by random linear network coding. Some people in the Ethereum community are working on this. There's a couple of, there's a project called Optimum that works on this as well. This is not ready yet in the sense that Byzantine attacks are absolutely murderers when you look at anything related to random linear network coding. There's mitigations, they are not completely obvious. Super interesting topic, come talk to me after this. So we talked a little bit about deduplication. So deduplication is this idea that, if you have a mempool, all the validators are feeding themselves on the same mempool, the same pool of transactions, you have a lot of deduplication. One of the relatively straightforward, and I know that Delta at least is working on this, ways of solving this is to assign transactions per round. So you have rounds of proposals in all those threshold logical clocks based, DAG-based algorithms. Per round to one validator and one validator only. You're going to hash your transactions anyway. You might as well say, hey, that number might be useful for something. Hash your transaction and the round with some source of shared randomness among your validators. And that will give you a random assignment of the transaction to a particular validator. Refresh that on every round. The rounds are roughly every 50 milliseconds. If you're looking at a small scale implementation, you're looking at roughly 100 milliseconds. So every 100 milliseconds, you're rotating which validator is able to propose your transaction. And as a result, you get Byzantine, you get censorship resistance anyway within relatively decent latency bounds. That requires a shared random beacon, which is not trivial, but this is a thing that a bunch of folks have managed to implement these days. Finally, and I'll go very quickly on this. In MEV, you folks have been looking at blind sequencing for DAGs, blind sequencing for single-purpose consensus algorithms because they do not have such requirements on bandwidth, mostly rely on threshold encryption. There's more efficient ways of doing this for MEV in particular, but the only message I want to give you today is really this idea that there's a tendency for every single chain to think that, hey, my consensus algorithm is going so fast, surely, there can't be any possible MEV. My order flow is going so fast, you can't possibly analyze the order flow. TradFi analyzes order flow on the order of microseconds, not milliseconds. So you can bet that it's possible technically. Whether people will actually do it is a consequence of how popular your chain is. Every chain, including Ethereum, starts with an MEV mitigation technique that consists in putting your fingers in your ears and saying, na, 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 can't hear you. And every chain learns to their sadness that no, actually, that might be a problem. Now, Ethereum has done that since the Flashbots paper, right? Flashboys 2.0 paper, sorry, that led to Flashbots. Cool. Solana is at the moment asking themselves around Jito being the relayer of the transactions for the whole chain. Maybe that's not the ideal situation in the world. And Sui is at the moment in the initial phases of discovering that no, actually there can be MEV despite our DAG multi-purpose consensus algorithm that goes really fast. You have a choice if you're working on a new or existing blockchain project. You can keep using the fingers in your ears and Nana can hear you, or you can be a little bit proactive in designing around this. So there's excellent work on dispersed ledger that can be completely translated to a DAG-based multipurpose blockchain. Basically, there's already some pretty decent work, funnily enough, out of Chainlink on this, as to how you can basically run a little bit of erasure coding that you find occurring once again. And funnily enough, it means for engineers like us, you can reuse erasure coding code that has been used for dissemination at a turbine, and then put it in your client code and get automatic MEV prevention. We will have the occasion to read all of those details on the slides. Let's move to a conclusion, finally. Okay, so we're in 2025. There's been great simplifications in multipurpose consensus and the implementation. The implementation itself are usable on a let's just fork it basis today. Everything is a broadcast. You don't have 20,000 messages, workers, processes. This is your consensus is one task managing one data structure in one little parked area of your memory that has very clear storage backend that allows you to get crash recovery. So the low-hanging fruit is not a multipurpose consensus implementation. This is the good news. This is pretty much done modulo a little bit of changes towards your epoch change on how to restart that consensus task with a bunch of different validators. This is done. The only thing you have to optimize now is broadcast. And that's really in the networking part of the implementation. So the low-hanging fruit is dissemination. Byzantine consistence broadcast we kind of skipped over. Ask me after the talk. You can even get MEV mitigation on high throughput DAGs. Cool. And that concludes my talk. Are there any questions?